Is everybody there?
I think we have everyone.
Okay. Well, good afternoon. Well, wherever you are. My name is Vladimir Labay. I am the chair of the Electrical and Computer Engineering Department. We're going to have a short little introduction to our department and our program. I have a few slides to prepare for you. I ask you to interrupt, raise your hand, send a chat, a message if you have any questions during the presentation. There will be a question and answer period at the end. We have also some other faculty members joining us this afternoon, and they're open to questions as well. So I'm going to share my screen with you, and this is hopefully you can see that screen now. It should be a title that says Electrical and Computer Engineering at Gonzaga University. We good?
I can see it.
All right.
Good.
Okay. All right. So, as an introduction, I just introduced myself. I said the chair of the Department of Electrical and Computer Engineering. My area of expertise is communication and signal processing. We have three other faculty members here, and I'm going to allow them to introduce themselves. We have Claudio Talarico, we have Yanqing Ji, we also have Steve Shenham. Steve Shenham's name is not on that slide, but he has a photograph of him in that smart antenna lab. That's his research lab. So let's start with Dr. Talarico.
Oh, hi, everybody. So as Dr. Labay was saying, my name is Claudio Talarico, and my area of expertise is in the design of electronic circuits, both for analog and digital applications, and specifically both discrete and integrated circuits. So the little black spiders that you see inside your all electronic systems that you guys have. And I'll pass to Dr. Yanqing Ji.
Hi, my name is Yanqing Ji. So my area is in bioinformatics and embedded system, and also higher level cloud computing. So in the department, I primarily teach computer engineering courses. So if you have questions regarding those courses, let me know. So this is my 13th year at Gonzaga. So I love this job, I love to work with students. So I'll pass to Steve.
Yeah, my name's Steve Shenham. I'm in that picture right there, adjusting an antenna with Bob Conley. And in fact, the background of my audio, or the background of my Zoom here is the inside of that antenna chamber. So part of what I do is antennas. I teach an antenna course and generally electromagnetics courses, and sometimes I teach things like electronics and signal processing and electromagnetics and things like that.
All right, thank you. All right, electrical and computer engineering. I was have the slide here just to give us a little perspective on what ECE is all about, electrical and computer engineering. I was asked to put a little phrase on who we are, and I was thought of immediately of the our group of ECE chairs across the nation, and we have a little tag that we use, and it's called "The Future is What We Do," and that is so true, because if I reflect on the past 100 years and what the changes have been done in this field of electrical and computer engineering, it's amazing from what it was at the turn of the 1900th century to what it is 120 years later. And our purpose as an ECE field, and I just made it the most general the definition that I could come up with. And I said DCE is a field of engineering that utilizes electrons in motion and electromagnetic fields they create to perform useful and meaningful tasks. And so that's basically what we do. We use electrons in motion to do perform useful and meaningful tasks. And I want you to think for a moment on where have you in fact used electrons today to do a meaningful task. Take a look at the Zoom meeting, for example, and look at all the things around you. Even the fact as I'm communicating with you, it's done through electrons in motion. The camera that you're looking at, the screen that you're looking at, the speaker that you're hearing my voice over.
Mom, you're not mute.
Hello? So there's so many different applications. So as I said, just look around you. What have you done using electrons for? Is it making a telephone call, sending a text message, heating up your food, or microwave, or your stove, running a motor, electric motor for your fridge, and the list goes on and on and on and on. And so when you think of ECE, think of any time that you in fact use electricity or electrons in motion to do something useful. That's a ECE engineer was behind that. Now, I would like to start off with a little bit of a description of what the first year experience would be at Gonzaga and what the curriculum is like. First of all, we have at Gonzaga is what we call a common first semester, fall semester for all engineering majors. And so every engineering major that comes in to the program takes the same set of courses in the fall semester. Our thought process behind this is that many of you, some of you may be undecided on which particular field you would like to study in. Some of you are not sure. Do you register for something, and then once you get to Gonzaga, you say, well, no, I think I have a better fit in another major. It gives you that time to be exposed to the engineering program and make that decision so that you could choose the right major and you have the time to do so. The spring semester of your freshman year is only one slight difference between the electrical and computer engineering programs right now, is that the electrical engineers take a statics class along with the mechanicals and the civil engineers, and the computer engineering class takes a computer programming class along with the computer science majors. So it's pretty much, you can say that the common freshman year is for double E's. There's one little small exception for the computer engineering majors out there. In that common freshman fall semester, we have a freshman seminar. We call it ENSC 191. It has a studio lab. It's 3 credits long. So that studio lab, which is the little photograph that you see to your right there, it's a little kind of a Arduino robot that they program to do various small little tasks in the studio lab. There's many things that are discussed in that freshman seminar, and one of them is to give you an overview of all the different types of disciplines of engineering that Gonzaga offers in mechanical and civil and electrical and computer and engineering, as well as the engineering management, and so that you can make that informed decision by the end of the first semester. The major topics in the ECE areas start in earnest in your sophomore year. We have a circuits class, 2 sequence circuits class for your sophomore year. Circuits is very important for ECE curriculum. It is the, I like to refer to as it being the language of ECE. And that's how we communicate ideas and thoughts as engineers to each other. It's through that understanding of circuits and those relationships that are dictated by those circuits that we have. We also have a intro course in digital design and microprocessors. Maybe Dr. Tarico can explain the digital design in the first digital design class. And I'll have Dr. G explain the microprocessors class in their sophomore year. Go ahead, Dr.
Yeah, so as Dr. Labay was mentioning, building circuits for performing all the spectacular tasks that he was telling you about is done through circuits. And there are like typically 2 types of circuits that electrical and computer engineers build. So the first category is it's what they are called analog, and so they have components that are resistors, capacitors, inductors, so something that reminds you more of components that the physicists invented a long time ago. And then there are digital circuits that mainly use transistors, and they use transistors as if they were switches, and that allows you to very, very quickly process any kind of information in terms of only 2 levels, 0 and 1s, and that is one of the major revolutions that have happened in terms of electrical engineering over the last centuries, basically, because more and more of the systems that are designed in electrical and computer engineering are digital circuits. Your computers is the typical example. Most of what we do is based on computers, no matter if you are building hardware or if you are writing software, everything relies on computers, and digital design is, or digital circuits is the basic founding blocks for building computers. And I'll let Dr. G tell you a little bit more about microprocessors.
I don't think your microphone is on.
Sorry. So a microprocessor is basically a digital system. In this course, we just look at a little bit high level about the architecture of microcomputer, like you have CPU, have memory. Also look at how the instructions for computer. We look at how the instructions are stored, how each instruction is executed. And more than that, we also look at how a microprocessor interact with other components. For example, for a cell phone, you have a keypad, you have kind of screen. Yeah, we just play with this. We look at how a microprocessor interact with like a keypad, LCD screen, or how to read information from a sensor. So we have a list of experiments. We just put different components together, but the key component is the microprocessor. And you need to understand this system. You also need to write a program so that the microprocessor can interact with different external components. So yeah, that's the microprocessor course.
Steve, you have anything to add? I think your mic's off too.
Yeah, my mic was off. There we go. Yeah, my mic was off. Yeah, I think Dr. Tallarico and Dr. G gave you a pretty good overview of some of the things. I guess one thing I would point out about electronics is you see this pencil right here? I don't know if yeah, there we go. The tip of this pencil, the very tip of this pencil could probably hold tens of thousands of transistors, perhaps hundreds of thousands on the tip of this pencil. That's a pretty significant thing to think about, especially when, 30, 40 years ago, we're using tubes that were this big, and they did the function of one transistor. So every 18 months or so, the size of things, the scale of integration doubles, which means everything gets half as small. They can fit twice as much stuff in the same amount of space. So memory is shrinking. Things are getting smaller and smaller. Electronics are getting smaller. More and more information is getting transferred from one place to another through the airwaves, and I think that's very exciting. And it's a good thing to learn about. And if you do, you'll never go hungry.
Thanks. I do have a couple of things to point out that are available to students in our programs. We have, like, for example, Dr. Shenham is situated in his antenna lab. He has often and continuously over the last several years have had undergraduate research students working with him in the lab. They evolved, some of them went on to graduate school to continue their work in antenna theory or in electromagnetics. Others have obtained jobs in the telecommunications area, wireless communications area. So there are those opportunities in our department. And there's other faculty members that do other types of research. And so Dr. Shim is not the only one. So that's something, if you're interested in doing, you can always contact one of our faculty members and see what type of research they are doing and whether that you can do some work with them. I don't know if I'll turn over to Dr. Shannon again. I don't know if he has anything to say with his experience with undergraduate research students. And
yeah, my students have done a lot of different projects involving antenna designs, and many of them have done senior projects based on these antenna designs, and some have traveled to international conferences to present their work. We've had quite a few have gone off and done that, and right now we can build we have a little type of Legos that you can build antennas out of Legos, and those are then you can take this antenna that you've built and you can put it in the lab and you can test it and see how well it performs. There's quite a variety of tests we can do we can go to a room with an antenna and we can tell how many cell phones are on, or how many cell networks are in the room, or how many Wi-Fi networks are in the room. We can go around and measure things like that. We've done project with students where we measured how well the emergency communication system works in a building. So we've gone down and we've been able to do these kinds of measurements and plot out how well the emergency and fire communication systems work. So we've had quite a bit of exciting work that we're doing, and now we're getting into 5G, and that's a very exciting bunch of work to be involved with as well.
On your screen, the middle picture is one of our former students, and a lot of times they get involved in some very interesting senior design projects, which happens in your fourth year. You can see that this particular student is holding a smart helmet for a cyclist to be able to communicate with vehicles around him. for safety reasons. So that was their kind of senior design project. It was only a couple of years ago that project was there. Other opportunities for students. There is our study abroad program. We find that our students, most of our students, that they want to study abroad, they go to Spain, in Madrid, St. Louis University from St. Louis, another Jesuit school, has a branch campus there. And they offer the full suite of classes that we do here at Gonzaga for that spring semester. And so if you choose to go there, you don't miss a beat. They have the laboratory facilities as well as the classroom facilities, and the courses being offered are the same as if you were at Gonzaga. And so that's an opportunity. The other one that we have a relationship with is the University of Auckland in Auckland, New Zealand, and we have some students who are there. And the same thing holds true there, is that you can go without missing any programs or any curriculum details that you have to make up when you get back. The third point I put on here is that there is an institute of electrical and electronic engineers. It's a professional institute. It's abbreviated IEEE, and it's a profession that's a professional society of ECE engineers, and we all have a student branch section on campus, and they have a lot of opportunities for extracurricular activities in the field of ECE. They get together monthly, or if more necessary, they have little projects going on. They have, they get together to study group sessions and things of that nature. So also the picture that you see on your left, I think that one's taken in Florence of the group that was in Florence a couple of years ago. Here I just wanted to point out, and you've probably seen something like this before in maybe the general introduction session. So I'm not going to spend a lot of time on this particular slide. But there is it's a chart here. I didn't modify it from what I got, but the chart here on the bottom kind of goes through how the university core and our core subjects are integrated into the engineering program itself. So this is a university core that every single student must take, and there's particular themes for each of the 4 years of your undergraduate, from understanding and creating all the way up to imagining the possible in your 4th year. All right. You might want to start thinking about, once you have an ECD degree, what kind of job would you end up in? And as I started out with today's talk, is that anywhere that electrons are used to do some useful task, you have an ECE engineer behind it. So, and that's a lot of different areas. And so I just kind of threw up some of the ones that came to my mind in some of the areas that you might find an ECE working in. And so, wireless communications to robotics, automation, control, computer architecture, consumer electronics, the energy sector, with the utilities, the power and the generation and the distribution of electric power, the grid, cyber systems. Some engineers find them in the sound industry, or in the medical instrumentation, imaging, the MRIs and the scanners that you have for the medical industry. Some engineers that end up in space exploration. They're working with SpaceX, for example, or NASA. We have a large area of sensing and radar applications. You know, you've heard about the autonomous cars that are being developed. Well, they have a lot of sensors around them and a lot of radar applications that for that to feed into the AI and the machine learning algorithms that are part of it. So those ECE applications are being used in those particular areas. Information theory and coding. Many engineers end up working in the coding scheme. You've probably seen some of the codes that we've have developed. You know, the MP3 players that's a code. It's a coding scheme for music and video. We have codes, numbers of different codes that are used for speech processing and video processing to reduce the amount of actual information that you need to store and to transmit. Embedded computer systems, that's what Dr. G teaches a course on that. He can probably explain a little more than I can on that. There's transportation systems. We even have engineers that go into the financial industry, and they apply our signals and system analysis to the financial world. There's integrated circuits, as Dr. Talioco has spoken of, telecommunications, automation and film, and the list goes on and on and on and on. So it's nowhere near a complete list. I don't know if there's any of my colleagues want to add a few more highlights that I've forgotten to mention here.
Well, okay, I will add something about, for example, the chip design. So every single line that you see there, you have a chip inside. And so the integrated circuit and chip design make sure that you learn how you can design and manufacture the chips that go in basically all other kind of application. Another application that it's electrical and computer engineers end up working very frequently. It's, for example, automation. Right now, there's a lot of great company like Tesla and so on. And I'll just give that to Dr. G in a second. But for example, if you think about a car, not very often you think about electronics, but there are typically, on average, in any car today, 15, 20 microprocessors, which are doing embedded computing. The automatic braking system is done with an embedded system. You have, for example, when you push the gas, there is a microprocessor that controls the pressure of you pushing the pedal, and that gives the correct amount of gas that goes and gets burned by the motor. And these are all, I guess, embedded system on which Dr. G can elaborate more.
As Dr. Talarico said, the embedded system is used a lot. Like each car may have dozens of embedded processors. Like the processor may collect the speed information, the gas level, and so forth. And it's used a lot. It's also used in many other kind of products, like a printer. You may have embedded processor, and like even microwave in the airplane. Yeah, it's used a lot. And also, if you choose computer engineer, you may just work as a software engineer, but your program may just be based on some hardware.
Thank you. Steve, anything to add or to go on? All right, this is one of my last slides before we go into question and answers, and I hope that you have a lot of questions for us, because we got a few minutes at the end of the hour to do that. I did want to mention that we have 7 different teaching laboratories in our department. And so we have a lot of lab experience where students get into the lab, they build the circuits, they test the circuits, they measure the different, they do perform measurements on it and on performance. And I've shown a few items in here is that you have the large picture on your right is the control systems lab, and the faculty member to your left that's in the forefront is Mary Zhang, and she teaches our power and control system classes. And there's a number of seniors. This is a senior level laboratory, and so there's a number of seniors working on their labs for that. So we have a communications lab where that's associated with our communications class. We have a controls lab, which you're seeing here. We have our basic circuits lab, where the first course in circuits, you have a lab associated with it to start building your own circuits and start performing measurements on there. Then we have an embedded systems laboratory, which Dr. G teaches. He might be able to speak more about that lab in a couple of minutes. We also have an electronics lab with both Dr. Tallarico and Dr. Shen teach. And I'll turn those labs over to them. We also have a microprocessors lab, but we spoke of microprocessors earlier today. We also have a digital system design lab, which Dr. Tarico spoke to earlier today. We also have a power and energy lab associated with it. And I think I hit them all. Isn't that? So the electronics lab, let's start there. What can we say about the electronics lab?
Steve, do you want me to talk about the electronics, or you want to talk about the electronics lab?
Or we can go to embedded systems lab. I think you've kind of described what you do in that lab already.
Yeah, I think you described the lab. I was up on campus today. I took a couple pictures of some of the labs. So if you want me to share my screen, I can put a picture up of any lab you want.
Sure. Why don't you?
Let me see what I can do here.
Do I have to take my sharing screen off?
I don't think so. Let's just see what happens. Also, if anybody has questions, you should feel free to belt them out. Let's see.
I don't think I have it set for you.
I think you may have to take off your screen so that Steve can share.
Let's see.
I'll stop my sharing, and then you should be able to share yours now.
Where's the share screen? There we go.
At the bottom.
Found it. Okay. Here's a picture of the antenna lab. These are some of the antennas hanging on the wall. That red thing is a log periodic antenna, and it can measure things from, I think about 200 megahertz up to about 1 gigahertz. So if you go into a crowded room, you can see everybody's cell phone with that one. It's kind of fun, and you can see all the cell connections and things like that. The other antennas, the horn-shaped antennas, are generally for higher frequencies and for narrow bandwidths. Anyway, that's a picture of that lab. Here's a picture of the inside of, those are the Legos right there that you can build antennas out of. There's some of them are metal and some of them are different kinds of plastics. So we can make different types of antennas out of those Legos. Here's a multi-axis positioner. So you see where the blue masking tape is on those 4 prongs that stick out there. That's where we put an antenna on, and then we can rotate it through every possible degree of freedom and see how the antenna performs in this chamber. So that's the small chamber, and it's, I don't know, what's it about? It's less than 10 feet long. The small chamber is. It's for smaller antennas. Now we have another chamber for bigger antennas, and that one, I thought I had a picture of that. No, this is the electronics lab. These aren't in any order. Here's a picture of the electronics lab. It looks kind of empty. It's sad because there's nobody in there. Anyway, that's the electronics lab. What else did I take a picture of today? Here's a picture of the embedded systems lab, and that circuit board you see there is something that you program when you're in the lab. You write programs, you send them to that, it turns on lights, it displays things, and I think Dr. G and Dr. Tallarico could say more about what these do. I haven't taught this lab in a long time, but they have been teaching it pretty actively lately, so they know what all these switches and lights do and how you can program them. Let's see, what else do I have here? This is the milling machine. This thing cuts through these sheets of copper, and we can make circuit boards with them. So if you have a circuit that works on the breadboard and you want to actually make a circuit board and solder parts to it, you can put it in this milling machine, and it'll cut and make the circuit for you. So let's see, there's that. I think that's all I'm seeing right now.
All right.
Any questions about any of that?
Well, there's a question that came up by Mike. That said, is field theory taken by computer engineering students or electrical engineering students? So, Dr. G, you can answer that question.
Yeah, I'm sorry. Can you repeat the question?
Is field theory, I guess you're talking about electromagnetic field theory, taken by computer engineering students or electrical engineering students?
The STEER theory?
Electromagnetic field theory.
I think that's an electrical engineering, right?
That's correct. So the answer to that question is the computer engineering students do not take electromagnetic field theory. What do you have instead of? That's in the junior year of the fall semester when they take the electrical engineering is taking field theory, and the computer engineers are taking what are they taking that semester? I forget.
Probably data structures and computer architectures. In general, I guess like the two curriculum and the electrical and computer engineering disciplines are very much interrelated and also multidisciplinary. So if you think about any of the systems that we were talking about, a cell phone would be a perfect example. Nobody really, it has the skills for doing everything. So you start from, for your cell phone, you start to receive the phone, and there is Steve building the antenna for it. And then later, I would build like an integrated circuit for trying to discriminate noise from the signal and amplify the noise. And then, someone like Professor Labay will come in and apply some digital signal processing for enhancing and improving the signals. And then, in some of the area of embedded system and computer engineering, you do a lot of the programming for some of the apps that you have in your cell phone. So I guess that's something also worthwhile to probably remember.
Thank you. So I'm just going to open my chat. I know there's a few more questions coming in. We have, so that's the field theory, is that the computer engineers do not take electromagnetic field theory. They have a number of other different classes that are taking, that are more related to their discipline.
But they can. They can if they want.
Okay. More of a personal question. How do you all think the new facility will affect the curriculum? So we're talking about the new ICE building, is that correct? Okay, so we have, I think it's going to benefit the school a lot. We have a couple of new labs that are coming in into the space that's there. We're expanding our circuits lab. And so we'll have a better facility for the circuits. And there's a couple other labs that are associated with our department. So not only that, we're going to move some of our existing labs into that building, that'll free up some of our space back in Herrick where it is now, and that we can convert then into more research labs and give you more opportunities to do some undergraduate research with our faculty. So it's kind of an exciting building to be coming online. Any comments to add to that? All right. Next question is that how many ECE students are there in the department? Well, there are about 120, I would say, in our department over the 4 years. So you're looking at, a class of 30. That's for the entire department. And so right now we're pretty much evenly split between computer engineering and electrical engineering. And so at the first couple of years, the courses are very similar in terms of digital design and microprocessors and signals and systems and probability. And so you have class sizes, 25 to 30. Circuits are also common between the two programs. But then as you get into your junior year and your senior year, there's quite a diversion in the classes that you take. Therefore, your class are reduced to half of that many students into your senior year and your senior design. All right. We have another question here. It is, how are classes typically run? What does the day-to-day look like for students? Who wants to take that one?
Well, you sit in a classroom and attend a lecture. Sometimes there's you sit and take notes. Sometimes there's demonstrations. Sometimes there's interactive things that the professor does with the class. It just depends on the professor and the class and how they run it and what they do. Some people use a lot of the overhead and special effects. Some of us not so much. It just depends what you do. And some classes have a lot of lab work with them that goes along with it, and others not so much.
Yeah, so Gonzaga runs on a kind of a schedule of classes, lecture classes on a Monday, Wednesday, Friday. There's a slot that you're given an hour per class. And so your lectures are 50 minutes long in Monday, Wednesday, Fridays. And you have 10 minutes to get from one class to the next class. On Tuesday and Thursdays, the day is broken up into 75-minute lectures, and you have another 10 minutes to get between classes. So you'll probably be assigned either, or you take a class on a Monday, Wednesday, Friday schedule, or a Tuesday, Thursday schedule. And so that's your lectures. So typically most lectures are 3 credits long, i.e. you meet for 3 hours every week, either Tuesday, Thursday, or Monday, Wednesday, Friday. The labs, most of our labs are 1 credit lab, and they are 3 hours long. And so they meet once a week for 3 hours. And so depending on what class you're taking, most of the labs are tied with a lecture class. So you're doing both the lecture class and the lab class during the same semester. And they would run, typically they run in the afternoons, sometimes in the late afternoons. Sometimes there's evening sections of those labs. So that's what the kind of the day-to-day look for most students. The next question we have is, are many of the core engineering classes or courses and labs offered in summer? There's a no. Put it simply, we offer very little engineering in our department courses during the summertime. What we find most students do is that if they want to free up some time during the school year, they could take a lot of the core classes, the university core classes, your philosophy, religion, etc., even your math. They offer classes during the summertime, and so you can actually take those classes during the summertime, and it kind of frees up some time during the academic year, the regular academic year. Next question, do students need to present lab notebooks from AP science classes in high school in order to gain lab credit for any particular class? And I believe the answer to that is no as well. Is that Steve, do you know anything about that?
I don't know anything about that. I mean, the only it might work for a chemistry class, but that would be up to the chemistry department to waive a class. For example, there's no electrical engineering labs that have equivalent summer courses that I'm aware of.
Or AP classes.
Yeah, AP classes is what I meant.
All right. So that kind of takes us to the last question. I'm going to open it up once again. Does anybody else have any questions? I shared my screen again, and I've given you emails for 3. Dr. Shenham's email is not on there, but it's his last name, Shenham at gonzaga.edu is his contact information. It's also available on our website. And I would say is that, if there is any questions that you have about our programs and what we have to offer, don't hesitate to reach out. And most of us are working from home, so email is probably the best way to get a hold of us until we reopen the campus for everybody. And I guess in summary, I think ECE is such an exciting field to be part of, and Gonzaga, we have experience in our department for most students that's outstanding. It's next to none, and we've got our faculty are devoted. They're available to students. We've got small class sizes. We got personal attention. And we're here to be for our students, and we are focused on our students as our undergraduates. And if we were able to put some other present students on there, I think they would tell you of an experience that they're not regretting that they came to Gonzaga for the ECE programs. Any conclusions offered for the other faculty? I don't think there's any more questions that are coming in, so.
We hope to see you all in fall.
Yeah, and if you're undecided, just check electrical.
Yeah, really, there is pretty much everything you can think of. It has some electrical and computer engineering component.
All right, I'm gonna, the monitor is, I'll turn it over to you. I'm not sure what to do now, so.
It looks like we have just Connor who wanted to say thank you guys for your guys' time and being able to help answer any questions. To all of the students that joined us for today, thank you so much. We will be, of course, posting this as a recording, and hopefully if you guys have any questions, as our professor Vladimir has mentioned, you're more than welcome to follow up and ask any questions to any one of our professors. So thank you guys so much. We'll stick around for a couple more minutes in case there's any last minute questions, but thank you guys so much.
Thank you.
Thanks for coming. Now, little rectangles are disappearing like mad.